Welcome, everyone, and thank you for joining. We will give it a couple of minutes for everyone to pile in, and then we will get going. Thanks again for joining. In the meantime, I will go ahead and launch a welcome poll. Please feel free. Please give us the information for the presenters to understand where you are in your Redis journey, what you currently know about Redis. Again, thank you everyone for joining. We are giving it a couple of minutes for everyone to pile into the session, and we'll get going at the 2 or 3 minute mark. Thanks again. Folks are piling in. I love to see it. Hope everyone's off to a good start in their day. As you join, please do go ahead and answer the welcome poll. And again, we'll get going shortly. All right, I will leave the poll up as I go through best practices. So feel free to please give us an answer, but I will get going and I'll shortly pass it over to the presenters. To begin, thank you all for joining and welcome to a Redis workshop. I am Camilo and I will be your host for the Vector Search with Redis workshop. As you join and settle in, please take a second to answer the poll on your screen. This gives us and the presenters an idea of your experience with Redis. Before passing it over to Eli and Tom, I will dive into some Zoom best practices. As you join, and as you may already know, everyone will be muted and off camera upon joining the session. Please note that this session is being recorded, and the recording will be shared with you shortly after the session, along with several takeaways and workshop items that Tom and Eli will be presenting. Please add any questions to the Q&A tab. That will give us a very clear idea of the questions we can answer live during the live Q&A at the end. For interactivity, please use the chat feature. As you join, please go ahead and tell us where you're joining from in the world. I am in New Montclair, New Jersey, and it is currently 12 p.m. With that, thank you again for joining. We're very excited to dive in. Over to you, Tom.
Thanks, Camilo. It helps if I turn on the microphone, huh? All right, let's get started. So we're looking at vector search and vector workshop. My name is Tom Solon. I'm senior training engineer with Redis. Presenting also some functional code examples will be Eli Cohen. That'll come a little bit later. We also have other people on the line ready to answer your Q&A as they come up. So we'll be answering those in the Q&A panel, as well as then summarizing some of the questions and picking up any missed questions at the very end in a general Q&A. So here's an oldie but a goodie. When is a door not a door? Answer, when it's a jar. When is text search not a text search? When it's semantic search using vector distance. I'm going to talk about the difference there in this webinar, among other things. Here's our agenda. First off, we're going to talk about what is semantic search. Then we'll get into some application development with Redis, focusing on document storage, hashes, JSONs, and then getting into search features and the search syntax. Give a quick overview of vector search, and then Redis Enterprise and vector search and how they work together. We have a brief discussion of that, and Eli will give you some actual coding demonstration. The slide deck will be shared with you in PDF form, and Eli will also share the Jupyter Notebook that he's using for the demo. All right, so what is semantic search, and how does it differ from plain text search? Let's look at an example using Cornell University's scientific paper archive. All right, so this is publicly available archive from Cornell University. And if I put into the search, explain vector similarity search and do a search, I get not terribly useful stuff, okay? Vector-like singlet quarks, a roadmap. Apparently it hit on the word vector. All right, now this is not especially useful. I would not go to Quarks for an explanation of vector similarity search. Maybe for a game of Dabo or a glass of Romulan ale, but not vector similarity search. U-spin CP anomaly in charm looks like it hit on the word similar. With vector search, now if I do the same search and this is a sample, we'll provide you the website for this so you can play with it yourself if you want, using Redis vector search. So now I do a search, Hugging Face, Ptolemaic indexing. It's not obvious what that's about, but if I go here, now that's much better. Paper discusses new family of bounds for use in similarity search. Turns out, hey, it actually is relevant. All right. So that's the idea with the vector similarity search rather than just plain text search. We're not looking specifically for matches on keywords. We're looking for the relationship amongst those words. This is basically the structure of that demo site that I just showed you. The text from the Cornell archive went through several sentence transformers. You saw I just picked the default Hugging Face, but we also had OpenAI. We transform each of those and we save their vector embeddings in the document, basically with the document metadata and some of the document data. Now, in real life, you would probably pick one model and go with it. But this does demonstrate something pretty useful, and that's you're not limited to one embedding value. So we've got 3 text embeddings, maybe in an e-com situation. Instead of 3 different text embeddings, maybe you have a text embedding for the long description, an embedding for the product photo, maybe another one for a demo video or whatever. And then when a customer searches for something similar to whatever, vector search can be used for that. So that's the foundation of semantic search, searching for answers based on the semantics of the question rather than on matching keywords. Now, let's take a look at the foundation Redis Enterprise. So we've got the basic concept of the Redis instance, single-threaded, community edition, source available Redis database, commonly referred to as a shard, specifically when it is in a clustered database. The Redis Enterprise database itself is not a physical entity. It is a logical entity that manages the entire data set across multiple Redis instances. Those instances are hosted on Redis nodes. All right, this is the physical or virtual machine or container that is running the Redis Enterprise services. So then the Redis Enterprise cluster is the collection of nodes that allow you to pool system use resources and support multi-tenant databases. You can have multiple databases. Let's dig a little deeper into that Redis Enterprise node. All right, we've got the zero latency proxy. All of the client requests are coming into the proxy and getting routed to the correct shards. Unlike the source available Redis, where you have to connect to the shard that has the data, the proxy allows you to connect to the database with a single endpoint. We also have a secured management UI and REST API that also makes our secure command line interface possible. We also have then the cluster manager, which is going to manage the transparent failover of any shards, proxies, or any other processes. That gets access to or allows you access to the Redis shards themselves. So some of the benefits of this shared nothing symmetric architecture. One of them is multi-tenancy. All right, so in this diagram where it says database A, database B, database N, we're not talking about just separated namespaces like in the source available Redis. This is actual separate databases that you can set up different access to, different controls, access control lists, RBAC, different accounts, everything. It's ideal for microservices. It's capable of running hundreds of shards on a single node. It gives you shard isolation, which simplifies rebalancing of cluster resources, maximizes your infrastructure utilization. The main components of Redis Enterprise then are this data management controller proxy, that's what DMC stands for, the cluster manager itself, and the REST API. All right, enough of foundation. Let's get the coding, right? So Redis is a data structure server, and the data structures use unique layouts and operations for storing and accessing data efficiently, often in milliseconds or sub-milliseconds, even for enormous data sets. For example, yes, we are key value stores, but the values aren't just strings. The different values are supported, lists, sets, sorted sets, hashes, and so on. This becomes especially useful if you're using Redis for query caching. So the data can often be stored and retrieved in native language-like structures without the added trouble of converting to and from relational database rows. So each item contains a unique key and an associated value. Each value has a particular data type and commands that operate on that data type. In this example, we see a hash, which functions like a hash map, if you will, of key value fields. Commands operate on the data itself, such as incrementing a field by a specific amount or adding a field and its value to the map. In-memory data structures are fast and compact, so Redis can be used as a database, a cache, message broker, session store, queues, stacks, time series data, geospatial data, and of course, search. Here's a simple use case. For some of you, this may be it. 45% of you said that you are currently using Redis for caching. All right. And that works fine with a simple string. Strings are key value pairs. You can set session variables, for example, or set a web page, save an HTML page, get, retrieves values. You can also set an expiration time, and so that the cache doesn't get stale. Looking at it in code, it would go something like this. All right, so you've got your set and your string value. This would represent an entire page. And in this case, we're using it for a particular user. We've constructed this data from the data record, from the session store, from the user record. It's a personalized web page for user one. We can save it, and since it's just for the single user, we're only going to, in this example, save it for 60 seconds, after which time it expires. Or if user one logs out, we can delete it immediately. We already know it's not needed anymore. In this lower box, we're looking at the same code using the Redis client library. Redis, and that is how it's pronounced. You don't get a lightsaber with this. Redis, like many of the client libraries, endeavors to keep their methods the same names, the same as the actual Redis commands, making it a lot easier for you to program. Redis.set, for example, to do a set. Redis.get to do a get. But let's get into something a little bit more useful. Redis is a document store, starting with hashes. So you need document. Let's say it's a product catalog, and each product has multiple characteristics: SKU, name, short and long description, size, whatever. You need high speed, you need low latency. Hashes are sets of field value pairs, like a Python dictionary or a Java map. Each set saves variables as fields. All right, so with strings, the command is set. As soon as your code says to do an H set, the Redis server automatically knows this is a hash. And so the commands are essentially type safe. HMGet allows you to get multiple, M as in multi, get values, or HGet an individual value from the hash. HIncreby to hash increment by a specified value, or HDEL to delete an individual value. Let's say, for example, we've got this starting hash where the name, SKU, department, price, we initially set these values in the hash. When we set that, the return value is the integer 8. That's how many fields got saved. Let's say later on, we want to add a long description. HSet product colon the number, and then long description and the value. You don't need to provide everything else. We just add that information. And a hash can be indexed for fast querying. We'll talk more about the syntax for indexing a little later. But wait, there's more. A hash can be indexed for semantic search too. Again, we'll talk more about the syntax for vector indexing later. The other option for document storage is JSON. So Redis JSON is a feature that fully implements the JSON standard, the ECMA 404 standard, which despite the number, I had no trouble finding this spec. It provides JSON path-like syntax for selecting elements inside documents. Documents are stored as binary data, but in a tree structure, allowing fast access to the sub-elements and providing you typed atomic operations for all of the supported ECMA 404 supported JSON data types. Here are the biggest value adds of JSON and Redis. Primarily, we're looking at atomically performing any JSON command, avoiding the memory and bandwidth overhead of serializing and deserializing complex objects, nested JSON, and multiple data types, including vector embedding. This is the JSON object that I'm going to be using in the coding examples and the rest of these slides. It's not what the actual coding is going to show, but this is what's going to be in the slide. Again, using that ecom example. So we've got in here strings, number, JSON, and even an array. Later, we'll add vector embedding, but let's keep it simple for now. JSON set, like with strings and hashes, set is, in essence, an upsert. If the value already exists, if that key already exists, it's an update. If it doesn't, this will be an insert. The actual process that the Redis server is going to do as it sees JSON.set product:1, first it checks if that key exists. If it does, this is an update. Otherwise, it doesn't insert. Then it goes to the path specified, in this example, root, and inserts or sets the values for these JSON. So if at that path, these fields or any one of these fields individually already exists, it will be an update. Any of these fields that don't already exist in that document will be inserted into that individual document. For get, so JSON.get with just the key name gets you the entire JSON document. JSON.get key name with a path to a specific field gets you that one field. You can get any nested property of the document by simply giving the path to that field, such as JSON get product:1 root.category.name. You can get any element of an array by specifying which element. In this example, the first element, root.tags square brace 0. The example we were looking at had an array of tags. If we want to append to that array, root.tags and the value. Increment a number, or decrement for that matter, it's num incr by the field and the value. That is to say, the value by which we're incrementing. Here, increasing the price by 10. But wait, there's more. JSON can be indexed for semantic search too. Again, we'll talk more about the syntax for that later. Let's first talk about search syntax in general. Before we get to that, in case you didn't know, Redis Enterprise provides real-time query and search, 4 times faster than results from competitive search solution. It scales. It's flexible secondary indexing, makes it easy to find and act on any important records and fields. It auto-index for accurate search in real time. What can you do with it? Standard querying on numeric ranges, tags, geoqueries. You can do full text search, including automatic document ranking by text frequency, inverse document frequency. You can weight particular fields. You can enable autocomplete suggestions. And of course, what this seminar is about, vector search. Semantic search for large unstructured text, visual similarity in pictures or even videos, and hybrid queries combining vector search and filtering on other fields. The basic concept is the index. Each document has an ID and an index, where you specify the schema for the index. In this example, we've specifically called out that the documents don't need to have all of the same fields. I can still index on color, even though some of my products don't have a color property. Last thing I want to show you before I go on to the syntax is that unlike in the Community Edition, Search and Enterprise supports clustering. Your index can be searching on data stored in multiple shards in the cluster. There's a coordinated component that coordinates the query execution by doing a kind of scatter and gather. Each shard has its own partial index, and by making use of the proxy, we combine those into a single logical index, allowing us to search the entire database. In order to create a schema, the command is ft.create. You specify the name of the index you're creating and what object it's going to be on. The options are hash or JSON. So on hash, prefix 1 product colon is only going to search on hash documents that have a key that begins product colon. If I had multiple prefixes, let's say product colon and service colon, prefix 2, product colon space service colon. That's simple. And then the schema. What are the fields? How are they being indexed? The same concept with JSON. Now it's on JSON instead. And instead of the name of a field, the path to a field. So root.name as name. With JSON, you specify an alias, which in these examples is not impressive, but if you had a more complicated structure, such as addresses.billing.postal code as zip, means I can do a search on zip rather than having to type all that path out. So creating a search schema always starts with modeling the data to be searched. So let's start by assuming that this is the type of data we have. So this is an example of a product and the fields that are in it. How would we index this? Here, getting a bit more complicated, we've got our ft.create on e-commerce products, on JSON, documents that begin with product colon in the key, SKU as tag. So SKU is alphanumeric, but it's not going to get changed. Tag is the most efficient indexing option. So we're going to do the stock keeping unit as a tag. The name is text, but we've decided no stemming. Weight 1.0 does not change whether or not this field is a hit. It alters the return sequence of values. So a hit on a field with a weight of 1 will be earlier than a field with a weight of 0.5. Color's a tag. Price is numeric and sortable. Now you can sort on any field, but if you know in advance that you're going to be sorting on it on a regular basis, you can flag it as sortable, and that sorting will be in the index too. Short description text, but we also want to allow phonetic search. And then as soon as we say phonetic, we need to specify the dictionary. In this example, double metaphone English. Long description is a text. Description embedding is a vector, and so on for the rest of the fields. but only the fields that are relevant for a customer search. These are the field types. Numeric fields, of course. Geofields, you can store longitude, latitude, allowing you to do geospatial radius queries, like, what's the closest distribution point to this customer, or what's the closest brick and mortar store to this customer. Tag fields, as I mentioned before, they are stored as is, no tokenization, no stemming, extremely efficient. Text fields, human language. And then vector, where floating point vectors that are generated by an external machine learning model. Just in case you weren't aware, Redis is not an AI engine. It's not a model. You convert your data in the model of your choice and save those vectors in Redis. And then we can make it easy for you to search that unstructured data. Indexing of a document that matches the prefix defined on the schema happens automatically. You create a document, it's added to the index. You change a document, it's updated in the index. You delete a document, it's removed from the index. So that's how we create an index. Let's take a look at the query syntax next. ft.search is the command, the name of the index, e-commerce products in this example, at field name : value. In this example, we will search for "to-it" in the name field. If we're searching on a numeric field, we specify the range. So here, looking for anything less than 250 in the at price field. I'm not going to read this table to you, but just to set your mind at ease, yes, there is syntax for doing exclusive searches, inclusive searches, unbounded, upper or lower, equal, not equal. You got the idea. On tag fields, you need to use the curly braces. And it does have to be a curly brace. A Mo brace or a Larry brace isn't going to work. So here, color is a tagged field. So at color : curly brace violet curly brace. We'll search for the violet tag. Without the curly braces, this search would not work because that would be a text search, and color is not a text field, it's a tag field. For geospatial, it's longitude, latitude, the radius, in this example 25, and then the units, in this example kilometers. The exhaustive list of units available to you are meters, kilometers, miles, and feet. Some of you are probably thinking, shouldn't that be lat long? No, it's long lat, because if you imagine a Mercator projection of the Earth as Cartesian coordinates, overlay Cartesian coordinates over it, longitude is the X value, latitude is the Y value. And in math, we do things XY, not the other way around. In this example, the index now is pickup locations because there isn't any location data in the e-com products index. For full text search, simply don't specify the field name. That will look for this text in any text field. So find household in any text field. The default separator is a space, and the space means and. So at field name 1, val 1, at field name 2, val 2 will be and. Color red and price between 25 and 75. Home in any text field and office in any text field, not necessarily the same text field. If what I really wanted was the literal string home office, then I need to put home office in quotes. And then I need to escape those inner quotes. Or if I use single quotes around the query, then the double quote is no longer a special character, so it doesn't need to be escaped. But one way or another, you got to get those double quotes around the exact phrase that you want matched. For OR logic, you need to use this symbol, a pipe or a bar, or as an old Java programmer, I call that OR. So now we've changed it by inserting the OR to color red or price between 25 and 75. Color red or green. Home or office, not necessarily both. To negate a search or negate a value, you use the negative sign. Pretty straightforward. You can put the negative either before the field name or before the value, depending on what makes sense. So for example, minus at color colon curly brace crimson, any product that does not match on color crimson, which by the way, without any additional search parameters, this is going to return everything in the catalog except those products that have the color crimson, including products that don't have a color at all, because that matches on not color crimson. This one is the word home is there, but the word office is not in any text field. For vector search queries, to be continued. First, let's make sure we understand what vector search means. Let's start simple. What is a vector? Put simply, it's a quantity that has both magnitude and direction. Speed, for example, 55 miles per hour is not a vector. It lacks direction. Velocity, such as 55 miles per hour north by northwest, is a vector. When displayed on a Cartesian graph, they look like a ray, but they're not. The vector's arrow only indicates the direction. It does not imply that the line segment keeps going on in that direction. Vectors come in a variety of flavors and dimensions. So here's a couple of 3D vectors, but that's a little hard to represent in 2 dimensions. It's even harder in 2 dimensions to represent vectors that are 4 or 5 or 128 or n dimensions. And 128 is actually a low-end number for text. So we're going to stick to 2-dimensional representations in these slides, even though they're really 64, 128, 512 dimensional vectors in real life. Use your imagination, okay? Starting with, imagine the results are something like this. We have 3 sentences turned into vectors on a graph. We can already see that similar starting sentences generate similar vectors, but we need a way to quantify that. Let's look at a few of the many that exist. So we discussed what's a vector. The next logical question is, what's similarity? Right? Where's Gomorrah? Now, who's Gomorrah? But we're computer programmers, not abstract artists. So similarity needs a numeric quantity. Enter distance metrics. These are the 6 most commonly used metrics. Note that each of these diagrams, of course, is representing the distance between 2 points, but the principle applies to vectors in n-dimensional space. I'll stick to a couple that are supported in Redis Enterprise. Euclidean. This is just like high school geometry class. Draw a straight line between the points and then use the Pythagorean theorem to calculate its length. It's sometimes called L2 distance, as in L squared, leg squared equal the sum of the legs squared equal the hypotenuse squared. And then cosine similarity is practically self-explanatory. We look at the vectors themselves and the angle between those vectors. The smaller the angle, the smaller the cosine, the closer the vectors are. Now, the calculation is a little bit more complicated than that, but that's the basic principle. Later on, we'll also see inner product, which is an extension of cosine similarity that includes the vector magnitude in the equation too. Now, because cosine similarity does not consider the vector sizes, it's ideal for comparing strings of different lengths and also images, videos, and other such sources of unequal size. Okay, we define vector, we define similarity. It's time for why is Gomorrah. Let's take a stab at defining a vector database. It's a database that can store vectors, but also index vectors and search the vector space. And it needs to meet the throughput requirements and be scalable and highly available. Let's talk about Redis and vector search. So we ended the previous section with a description of what a vector database needs to handle. Does Redis meet those requirements? Yes. I mean, come on, this would be an awfully short presentation if the answer were no, right? Redis can store and index vectors. Vectors are stored in a hash or JSON document. There are two indexing methods, flat and HNSW. I'll tell you what that acronym means in a little while. And several distance metrics are supported, specifically L2, also known as Euclidean, IP, which stands for inner product, and cosine, which of course is referring to cosine similarity. We'll discuss these metrics and methods more in the upcoming slides. So the vector indexing algorithms, there are two. There's flat, which is a brute force approach, and HNSW, hierarchical, navigable, small world. And if anybody starts singing, I am going to pull this webinar over and we're not going to Wally World. So HNSW is faster, but only approximate. You can think of it kind of like a multi-dimensional analog to a skip list. For vector search distance metrics, you choose from Euclidean, L2, inner product, IP, or cosine similarity. We also provide hybrid filtering, allowing you to filter the documents first on standard things like tags or text or numeric ranges before doing the more resource-intensive vector search on the remaining values. We also provide real-time updates. Documents change, images change, text, product data, metadata, dates, whatever. With Redis, every time you do a update, insert, or delete, if it's an affected index, it is seamlessly, automatically updated. And then vector range queries. Most vector searches do top K. We have that, and we also allow you to specify a range. So top K is, find me the top 10 answers, the top 5 closest matches, the top 3 closest images, whatever, top K. We also allow you to specify a range. So instead of saying, show me this particular number of items, show me any items that are within a threshold. So you can use Redis as the database for high quality, high speed similarity searches. The idea is, as I mentioned before, you've got some external model. Your audio goes into the audio model, which creates vector embeddings for that and can be saved. Text into a text model, videos into a video model, images into an image model, and so on. Let's take a look at text semantic search next. So here's the basic process. Let's assume you already have a collection of documents that varies depending on the use case. But maybe in yours, it's a product documentation, or maybe just the product catalog, all right? Or operating procedures, or billing history, whatever, all right? First thing you need to do is watch out for document length because models typically have a size limit. If necessary, you split the document into chunks to stay within those limits. Then you store the original document and metadata in a hash or JSON along with the embedding. Then if your user, customer, whatever, is looking at a document and asks for similar documents, recommendations, or other help articles, whatever, again, whatever other products, you've got the vector embedding for the current document already. So you do a similarity search and find documents that are similar. You can also do a hybrid search if, for example, they're looking for new products or recent additions or whatever. Visual search next. Again, similar idea. You use a service to calculate the vector embeddings, store the embeddings with the image metadata. Images are typically stored elsewhere. And let's say in this example, we're generating vectors for product images in our catalog. In that case, we'd store the embeddings with the rest of the product data to facilitate hybrid searches, like we saw in the earlier slides, depicting long description and its embedding in the same JSON, as well as the prices. Then let's say a shopper comes in and says, hey, I want to buy one of these, and uploads an image from their smartphone. You use the same image processing service to calculate the vector embedding for the test image. And then that embedding is compared to the rest of the vector embeddings with vector search. You could also filter results, limit the number returned, perform hybrid searches, and so on. So that's an e-com example. Another use case, a customer might take a picture of a malfunctioning widget, and your Redis database matches that to an image widget troubleshooting library, or identifies the part number, or you get the idea. Time to take a look at the syntax. Let's make sure we understand our terms. Again, flat, one of the things you're going to have to do is specify the indexing method. Flat is that brute force. HNSW is an approximate nearest neighbor search. K nearest neighbors, KNN, will find a specified number of neighbors, or range filter allows you to search for ranges. These are the 3 distance metrics. I've told you that a couple of times. We'll see it a couple of more times in the slides. So to create a schema, notice I'm intentionally picking the e-commerce products schema. What I want to point out is that this is going to be in the same index as all of the other product data. So we'll be able to filter on price or color or any other feature. So it is the path, in this example, root.description_embedding as what we want to call it. Not feeling particularly creative today, we'll just call it desk embedding. It is a vector. We're going to use flat indexing. 10 simply means there are 10 more arguments coming. Type. Currently, we support float 32 and float 64. Dimensions. Type and dimensions are always going to match the model. All right, so if your model is spitting out float 32 values in 384 dimensions, that's the values that go here. If it's spitting out float 64 in 512 dimensions, those are the values that go here. All right, that's the thought process that goes into this. And then the distance metric. In this example, Euclidean, L2. Optionally, you can set the initial cap size and block size. What most people do, and the safest thing, is to not specify them initially during your development. Accept the default values and then fine-tune as necessary on your way to production through testing and such. So now the vector search query. First example, KNN. We want its square brace first. KNN, that's the search we want. What is K? 5. We want the 5 nearest neighbor. The field name, and then a variable that points to the actual embedding that you want inserted in this search. And technically, that's the end of the query. Then comes the parameters. And in this example, we only are passing in one parameter, the value of my blob. And this will be the vector data. So for example, if a customer is searching for a picture that matches, a product that matches the picture they just uploaded, it will be, you've run that picture through the embedding service. Or if it is a description, they're describing the product they want, or let's step away from the e-commerce, they're describing the problem they're having and going through your debugging wizard. You've run their question or their problem through the model, and that's what the variable is going to be. Then in the code, or in this case, technically command line, it might look like this. So that is a happy person. We run that through the embedding model. We come up with a vector. FT search, my index, KNN, @vector is the name of the field. $B is the name of the variable as score. 2 parameters. B is that exact vector. And then the second parameter is sort by score ascending. And here's an example of the returns. If you're doing a search on range, instead of KNN, it's vector_range. Then at the field name, and now for range, it's always the radius. Now you need to be careful with the radius. It needs to match reasonableness, right? You're responsible for your own reality check. So if it's a cosine distance, the value will always be between -1 and +1. If it's an inner product search, It could be anywhere from negative infinity to positive infinity and beyond. So you're responsible for making sure the radius makes sense. And then the variable. And again, the params and passing in the vector data. For a hybrid search, here's the surprise for you. These technically were already hybrid searches that I was showing you. Search on star and pipe that through this vector search. So the hybrid query is that just instead of a star, you put in any valid standard query. So here at color, red, and at price between 25 and 75, take that smaller sample and run it through this, in this example, KNN search. So any valid standard query in parentheses equal greater than any valid vector search in square brackets. Let's take a look at some large language model use cases. First, what are they? They're massive general purpose neural networks pre-trained on large amounts of text, but not necessarily your text. They are specifically focused on language understanding and generation, commonly using vector search to retrieve information from external databases. Putting a vector database together with a large language model, there are three common design patterns. Retrieval augmented generation, where we're going to search for relevant sources of text from some knowledge database and provide context to the LLM. LLM memory, persisting the conversation history, and LLM cache. Let's take a look at RAG first. So the idea is we've got this question coming in. Which country won the most gold medals at the 2020 Summer Olympics? Potential problem with this is, what if this model was trained in 2020? Because the 2020 Summer Olympics didn't happen until 2021 because of COVID, which means that information is not in the large language model. Nonetheless, we can get it vectorized and have our own store of embedding. Like, for example, in this sports thing, perhaps the annual almanacs going back to before the model was trained. Then this search goes first in your Redis vector database and finds relevant documents from the sports almanacs. That is then provided as the context. That goes in these curly braces here before sending, given the context below, answer the following question to the LLM, which can return the answer. And now, even though it wasn't trained on the data that has the answer, it can find the answer in the context that you, as the programmer, provided. For conversational memory, Eli's got a great example of this in the demo coming up. LLM doesn't have memory as an inherent part of it. And so if a user asks a question, I don't know, maybe well, if you've ever dealt with customer service before, you have experienced this, right? First, you go through the electronic prompts where they ask you your account number and your password and your PIN and blood sample and whatever else. And then you finally get to a live person and they say, what's your account number? Because the system had no memory of what happened before. LLM conversation memory allows you to have a theoretically infinite contextual memory. So you can record everything that happens, make vector embeddings, and store that. With semantic caching, this is especially good use case for Redis, purpose-built for this. I mean, battle-tested caching and vector database, right? So LLMs are expensive and time-consuming. You can use a vector database to cache the input and answers. So let's say we've got a user that says, how can I reset the system when a C384 condition is detected? That goes into the application, but before we invoke the LLM, we go to our semantic cache and do a vector search on the question. And let's say we find in the vector database, how do I reset the system after detecting a C384 code alarm? Which is, in this case, let's pretend it is within our radius of search. We decide that's the same question. Now we return the answer to this question, which we've also stored in the database, to the application, which returns the answer to the user without having to go through the LLM. One last example I want to show you is going to be using this idea. So we've got another sample site that has, it's a mock e-commerce site. So it's got a whole bunch of products. We have run the descriptions through sentence transformers and embedded them. We've also run the product images through a separate model, transforming them into vectors. And both of those are saved with the rest of the product data. We're going to be going into basically a website React front end that has Redis Pi asynchronous backend that will search the Redis database and find similar products and return them. All right. So let me get to the right tab here. Oops, that's that there. So let's say I want to find tops similar to this one. I can search by text, the description, or by image. Let's do by image. That's, I think, a little bit more interesting. And so I see a bunch of tops. I think it's kind of interesting. Notice that the top hits, the women are also wearing shorts because I said, give me pictures similar to this. I didn't narrow it down to tops. And I finally see down here, we have a men's top that's also striped. I want to call to your attention 40,000 searchable products. That's what this value was returned on. And you probably noticed really quick. But what I can also do is apply a filter. So let's say I'm into men's clothing right now. And then I can search on this same image, and the return results don't even include my initial image because that isn't in the men's department. And now I have a whole bunch of horizontal striped shirts that are in the men's. And the most important thing here is that that was a search of only 20,038 products. I did narrower search. Fast results, I mean, with just a mere 40,000 images, it didn't take long to do the search anyway. But if you've got something like the Cornell University Archive doing semantic search on huge amounts of text, you will appreciate being able to narrow down by publishing year or department or whatever. That's the power of hybrid search. I'm done. I'm going to turn this over to Eli, so I'm going to stop sharing.
Thank you, Tom. Let me share my screen. All right. So I want to show a demo of several of the use cases that Tom mentioned. Specifically, we'll talk about 3 use cases. One is semantic search or vector search with RAG to chat with some kind of a knowledge base. It's a pretty common use case. You have a bunch of documents, chat messages, user posts, whatever documents you have in your database, and you want to kind of chat with an AI based on this context. That's what RAG is for, and I'm going to show an example of how that works. And then next we'll talk about semantic cache, which allows you to cache previous results that an LLM returned and potentially retrieve and return them based on other users' questions if they are similar enough to that answer's question. So you don't have to go query the LLM. It's much faster, obviously. It reduces your cost because you're not actually using another API call to the LLM with all those tokens. You're just retrieving it from the cache. And then the third use case is chat memory. As Tom mentioned, LLMs don't have memory. Whatever you put in the prompt is the only thing that they can respond to. Chat memory is something that allows you to chat with an AI in a more human-like manner where the AI or the LLM will basically have context of your previous messages and can answer based on that context, so you don't have to provide it from scratch again. For this demo, we will be using LangChain, which is a pretty popular library for developing AI applications. And of course, Redis. You can create your own Redis cloud database for free. There's a free plan that you can sign up for and take it for a spin. For the RAG demo, we do need some preparation first. So the preparation we're going to do, which is what you will need to do if you are using RAG use cases in your application. So if you want to chat with your database or document store, is load the documents and then usually split them into segments. So let's say I have a document that is an 80-page PDF document. I can index it and store it as a vector, but when I retrieve it, putting an 80-page document into an LLM prompt is expensive, and it's also inefficient if the information that I'm looking for is just in a couple of paragraphs in the document. So what we're going to do is split the document into sort of chunks, and then we're going to transform each of those chunks into vector embeddings. And then we're going to store both the text and the vector in Redis search index. After that, we will be able to use LangChain to retrieve the proper documents based on the user's question and send it back to the LLM so that it will have context. So that is what RAG stands for. First, we're retrieving those documents, and then we're augmenting the generation of text that the LLM is doing with these documents. And then, of course, we will look at semantic caching and chat memory. Both are also using Redis features. And this code, of course, will be available after the workshop in a GitHub repository that you can use. There's instructions on how to run it. It's pretty simple. First, we're going to install some requirements. These are already installed, so that should be fairly fast. Download any models that we're using locally. All right. And then we're going to do some prep work. So we're importing some utilities that will help us to view the output in a more user-friendly way and download whatever files we need locally. So for the RAG demo, we need to go through that data preparation pipeline. For this demo, what we're going to do is chat with a couple of documents that are Redis search documents. You see this URL, it's publicly available. You can go look at it. This is actually part of the Redis search documentation that you can find in redis.io. And if you go to these pages, you can see that they are very long and very detailed. They will explain all about the aggregation functionality, what kind of functions you can do in aggregation pipelines. This one will talk all about the query syntax, the fields, the dialects. Very complex and very long, great reference, but I don't feel like reading all these documents if I just want an answer to a simple question. So what I'm going to do is download those documents. They're markdown, so pretty simple text overall. And then load them, split them, and embed them into vectors. So first, I'm going to, just FYI, I'm using Redis Insight to look at the database. So right now, it's empty. There's no keys here at all. And I'm going to download those documents locally, loaded 2 documents. And then next, I'm going to use a splitter. So this is a text splitter that will split those documents, those long documents, into chunks. And you can specify, you can use various splitters. There's a lot available just out of the box. Each of them might have, different strategies depending on your input, depending on how large the chunk of a chunk you want to have. This one, I'm going to use a chunk size of 750, so about 750 words, with some overlap. So, 50 of the words might be overlapping between chunk 1 and chunk 2, just for continuity. And then it's going to split the documents, and this splits is going to be basically a list of chunks from that document. So we loaded 2 documents, and then we are splitting them, and we got 67 splits. So splits is now a list of documents with 67 parts of those 2 documents. Next, we're going to create an instance of our embedding model. Our embedding model, in this demo, I'm using Vertex AI, which is using Google services like Gemini for the LLM. And pretty much every service that has an LLM has one or more models that allow you to create embeddings. So that will essentially transform the input to a vector. You can use local ones from Hugging Face or other libraries that are free and are simple. Just make sure that you are embedding your documents and whatever you use in your application, so the user's questions and everything, using the same model. So I'm just going to create the very simple embedding model with the Google services. This is just authenticating and creating an instance. And then the next step is I'm going to create a vector store. So my environment is already configured with the Redis URL. So when I load this Redis object and I run the from documents function, I'm going to give it a few parameters. One is, what are the documents that I want to index? So the documents are those 67 splits that we got after splitting the big two documents, the embedding model that I want to use, and a name for my index. What it's going to do is it's going to take each of those splits, run them through the embedding model to get a vector, and then save both of them with potentially an additional metadata in a document in Redis in an index called Redis VS Docs. So this is all being done under the hood. You just need to run this one method and give it your documents in your embedding model. It will do the rest for you. So before executing this, we have no keys in Redis whatsoever. And then we'll run this. It's going to take a few seconds. And now we have 67 documents here. So if we look at them, each one of those contains a few fields. One is the source field. So this just contains the name of the file that we loaded as the document. Potentially, depending on your application and your use case, you can have additional fields here and then do a hybrid search with some metadata filtering, like Tom demonstrated with the fashion store. So you can first do a metadata filter on one of the fields and then do a semantic search on the documents that were retrieved. And then the other fields are the content itself, so the actual text from the document, and the vector, which is the vector representation of that content. And then what's going to happen when we are running this RAG pipeline is the user is going to ask a question. We are going to do a vector search on that index. The vector search is going to find the documents whose content vector is similar to the question. And then it's going to load the actual content of the document and send it to the LLM so it has the proper context for the question that the user is asking. All right, so we have the index, we have the documents. Let's ask a simple question. How do I load the Redis key name or document ID and filter results based on that field? That's our question. And then we're going to run similarity search with score with that question. And k equals 3k is basically the number of results that we want to retrieve from Redis. If you remember in Tom's presentation, KNN stands for k nearest neighbor. So we're going to find the 3 nearest neighbors to the vector version of this question. So let's run that. And we found pretty quickly a set of documents. You can see the scores here. Lower is better. Lower means it's closer to the question. So you see the first one is the lowest. And I can already see that the answer is here. Now let's see how the LLM responds with those documents. Another kind of vector search is called max marginal relevance. It's very similar, but it does some sort of filtering based on the documents that were retrieved. So let's say you have the same paragraph of information that's repeating in your documents, or something similar. So you have the same information over and over in your document store. What MMR does is it takes a set of documents. So top K would be 5. So it will take 5 documents. And then it will run another kind of like similarity comparison between those documents. And it will only pull the 3 documents that are the most different from each other. So you don't have the same information repeated over and over in your context to the LLM. So if we run this, similar results altogether, kind of almost the same documents. So let's do some, LLM inference. Let's talk with an AI. First, we're going to create a prompt template. So this is what's going to be sent to the LLM. You can give it some sort of instructions. So you can tune this to your use case or to how you want it to answer. And then we're going to give the context, which we retrieved from Redis, and the question that the user asked. And the instructions are very simple. Based on these pieces of context that we provided to you, answer this question. Okay. We're going to create a prompt template that specifies that the parameters that we have here are the context and the question. So when we run this, it'll know to put the text in the right places in the template. So let's run that. And then we're going to use a chain that's called retrieval QA. So it's going to run retrieval, and it's a questions and answers chain. You can also use other types of chains. For example, if you're just doing a chat, you might want to use a different component that's not just questions and answers, but it'll give you a more chat-like interface. So for the model, we're using Gemini Pro, again, using the Vertex AI services. And we're specifying the output tokens and temperature. Output tokens tells the LLM how many tokens, which are more or less words, do I want in the output. So I'm limiting this to 512 tokens. I don't want a response that is too verbose or too long. I just want the answer. And then temperature determines how random the answer is, which, if you've seen those controls in chatbots, kind of correlates to how creative you want it to be. So a higher temperature, so let's say if I put this on 0.8, will be more random or more creative. A lower temperature will be will give a more kind of repeatable answer or predictable answer. So I'm creating an instance of this LLM, and then I'm creating this chain using the LLM object, the vector DB as a retriever. I want to see the documents that were retrieved, and I'm creating a chain type that's called stuff. And that's stuff not as in things, but as putting something into something. So we are stuffing the prompt with the documents that we retrieved from Redis. So we created this LLM instance and this chain. And now let's ask the same question to the LLM. The document ID can be loaded using @__key. And then we can, filter the results or do something else with it. Great. One sentence, just the answer that I was looking for. One of the services that we're using with LangChain is called Langsmith, which is kind of like a monitoring or debugging or observability solution, which is also free. There's like a free token limit that you can use while developing the application, and you can see what happened behind the scenes. So let's go there for a second and look. So we have this retrieval QA, and in it there are two steps. One is retriever that took 0.2 seconds, so 200 milliseconds, and it returned these documents based on this input. So it took this input, converted into a vector, and then ran a vector search and returned these sets of documents. And then the next step is taking those documents and stuffing them into the prompt. So if you remember the prompt, using the following pieces of context, answer the question at the end. These are the documents that we retrieved. And then the question itself, and the answer is what the LLM returned based on that prompt. So it's very nice to see what's actually happening behind the scene. We'll look at it again for the next use case. So that was semantic search or RAG. Again, very versatile use case. There's multiple types of documents that you can use with that, not just text. You can use image, audio, all depending on the kind of embedding in LLM that you're using. The code would be fairly similar, I would say. So embedding would still run an embedding based on an input and output a vector. The retrieval from Redis would be very similar. So you see we wrote almost no Redis code here. Everything was just done automatically behind the scenes. The next use case we're going to talk about is semantic cache. So as Tom mentioned when he started the presentation, text search and semantic search are two very different beasts. So with text search, you take a few characters or words and you search for the exact match in your documents. You can, there's obviously various strategies that you can use to fine-tune that to find the relevant documents. Semantic cache uses semantic search. So what you're looking for is not pieces of text, it's the vector. And in this case, the vector is the question that the user is asking. So what we're going to do is create an instance of Redis semantic cache, and we're going to use it as the LLM cache in our application. Again, we're going to give it an embedding model because it needs to transform these questions that the user is asking into vectors. We're going to give it the Redis URL and the score threshold. So what is the distance between the question that the user is asking and a question that's already cached? And that is the vector distance. So the smaller this number is, the closer the question should be, and the higher the score threshold is, the less similar those questions are. So if I put here 0.5, it might return a lot of results from the cache, but they're not going to be very relevant to the question that I asked. So this is something to play with and to tune based on your use case and application. So I'm going to use this as the LLM cache. And then I'm going to ask it a question. How do I get documents within a certain radius from a point? Run the query and see that it took 2.5 seconds. Very simple answer. At field, colon, square brackets, longitude, latitude, radius, and then your units of measurements, meters, kilometers, miles, or feet. Perfect. That's exactly right. And I don't really need more than that. And then let's say later on, or a different user comes in and asks a similar question, but with a different meaning. So instead of a point, we're saying coordinate here. So how do I get documents within certain radius from a coordinate? And I'm going to run that. And you see the previous question took 2.5 seconds to respond. This one took 427 milliseconds, gave me the same response. And let's see what happened behind the scenes. So behind the scenes, we see a couple of more, excuse me, retrieval Q&A chains that were created. So the first one, you can see the retriever retrieved the documents and then send it to the AI, and we got this result. In the second one, where is the second one? I'm not sure why I'm not seeing it. Oh, that's the one. Sorry. So this is the second one. And you see that there's only one stage here, only the retriever. So when you ask that question, it went to Redis, it created a vector out of this question, and it tried to find a similar question in your semantic cache. It found a similar question. So what happened is it returned the result of that question instead of going to the LLM and sending that prompt to get the question. So you see, it's not only much faster, but it saved you a call to the LLM that you are most likely paying for. So that's that's how you would use semantic cache in your application. Very useful, very little code. Basically, we just created an instance of Redis semantic cache and defined the embedding and the threshold. So, how accurate we want our cache to be. And then the last use case we're going to talk about is chat memory. So chat memory, again, if you're having a conversation with a chatbot or an LLM, would allow you to ask questions based on previous context in the chat. So if I'm telling it some kind of information about who I am or what I want to do, and then I'm asking some arbitrary question that doesn't include any context, it will still have the context because it has the memory and it will know how to answer my question. First, we're going to clear the LLM cache. And then first, we're going to look at a chat without any memory. So very similarly, create an instance of the LLM, create a template. If you see the template here, there's no context. It's just the input from the user. So we're creating a prompt template and an LLM chain based on the LLM object and the prompt. And then next, we want to predict the answer. So this is basically your chat interface. Hi, my name is Eli. I like eating noodles and I work for Redis. What is your name? And then we see it highlights, nice to meet you. My name is Bard. I'm a large language model trained by Google, blah, 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 blah. And then who won the World Cup? Great. It was won by France. And then another question, what's my name? Sorry, but I don't have access to your personal information. And if you notice, when I created the LLM instance, I put in verbose equals true. And what that does is it shows you not just the answer, but also everything that was sent to the LLM. So you can see here, we have the prompt, question, the answer. Prompt, question, the answer. No context whatsoever. So based on this question, what's my name? For the LLM, this is the first time that I'm interacting with it. It has no memory, so it doesn't know my name. Now we'll show an example of chat with an LLM with memory. So very similar, an LLM instance, a template. This time, I'm going to put a history variable here, which will store basically my chat history with the LLM, so it can use this history as context for the conversation. The way we'll do this is create an instance of Redis chat message history with a certain prefix and session ID. So you can create multiple ones for multiple applications or multiple chats or multiple users, and they can all be stored separate from each other. And then we're going to put it in a conversation buffer memory. So what we're saying is we're going to have a conversation, and we want some memory for it. Use the Redis chat message history as the buffer, as the memory for this chat. So we're going to create all those and then create another LLM chain. Okay. And then let's have a conversation with some context. Hi, my name is Adam. I have 3 kids and I like gardening. What is your name? My name is Gemini. My large language model. Great. No history in the first response. And then how long was the last Harry Potter book? You already see the history, so both the question and the answer from the previous chat. And then we get the answer. The last Harry Potter book was published in 2 volumes, this pages and this many pages. And then I'm going to ask a question that without context, we won't be able to answer. What's the name of their school? So if I just started a conversation and I'd ask, what's the name of their school? The LLM would be like, what school? What are we talking about? I have no idea. I have no clue what you're talking about. But since we have context, it can take that context and then use it to answer the question. So sometimes it will not have sufficient information, for example. So it doesn't remember, for some reason, what is the... So let's see if I run this again. And then school, nothing. Not sure what's going on there. It might be some tuning with the temperature or message history. So let's see if we're changing that and just running those questions again. And all right. So the only thing I did was adjust the temperature. here, just from 0.2 to 0.3, and then suddenly it got a little more creative with the answer. So what's the name of their school? The name of the school in the Harry Potter series is Hogwarts School of Witchcraft and Wizardry, which is correct. The next one is going to be a similar question that has no context, so it would have to remember the context from the chat memory. What train platform was the train on? Platform 9 3/4. Great. Based on the context, I got an answer. And then, do you remember my name? Yes. Your name is Adam. You have 3 kids and you enjoy gardening. So that was a demonstration of what it looks like to have a chat history and to use that as context to have more fluent chats. And you can see how variables like the number of tokens and the temperature can affect the result that you're getting. If we go back to Redis and we look at the documents here, so let me just refresh that. So we see the documents from our RAG use case. We have a cache here with a different set of documents. So this is what was cached using the semantic cache use case. So you see the prompt and the answer and the vector. This is what was used. And then we also have a chat history that is a list of messages between me and the LLM that we can use for our context for the conversation. And that was it. Those were the 3 use cases that we mentioned. All right. So,
Thank you.
let's see. Q&A. Can the vector store be created in an additive manner? So the vector store is, want to answer it live. The vector store is just like any Redis search index. The only difference is that one or more of the fields in it are vectors and not text or numeric or geospatial. And what happens with Redis indexes is that whenever you add a document to Redis and it has the right prefix for the index will automatically add it and index it. So as soon as the document is in the database, the information can be queried in the vector store. I hope that answer the question that was asked.
Another question came up about history. And if the history gets long, that could end up being a lot of tokens that are getting passed.
True.
Yes, we have the example Eli showed you was really simple code.
Yeah.
You could add another step where we're actually also embedding the vectors for the history and then searching for relevant history and only including that in the context.
Yeah, so it's a good question. This chat history, I think, was limited to, I think by default is like the 10 last messages. There's various strategies to deal with that. One of them is doing some sort of compaction. So let's say you have 10 messages and that's something that you would need to build or use like a library or component that is out there, and there are a few. You will take those 10 messages and you will compact them to one paragraph using an LLM, for example. So you will take those and send them to the LLM and tell it, give me a summary of those messages, and you'll save that in your chat history for context. So there's various strategies. That's just one of them of dealing with the history size. Let's see, any other questions? So let's see, can you explain a bit more about how the context and previous Q&A is passed to the LLM? Does it get passed as embeddings or natural language? Can we minimize the context so we don't hit the token limit of the LLM? Good question. The answer is, at least for text LLM, so chat and Q&A, it's natural language. It's not the embedding that's being sent to the LLM. The embeddings or the vectors is how it kind of works internally and how we're using retrieval with Redis. So where all of the searches that we're doing, all of the retrieval is based on vector search and not like text search or numerical search. So during the search, we're using the vector embeddings. What we're sending to the LLM is what's in the prompt. So it's the natural language of the document that we retrieved using that vector embedding. Minimizing the context so we don't hit the token limit of the LLM. So again, there's a lot of different strategies for that. You can limit how many documents you retrieve. You can limit you can change the size of the chunks when you split those documents. There's a lot of different strategies, and there's only more and more being thought of every day. So some of them are just plain all use smaller chunks or smaller message history. There might be more sophisticated ones in some tools or libraries. All right. Were there any other unanswered questions?
No, Eli, I think we have covered them all either through the live Q&A or panelists host have been answering them throughout the session. So I think we've answered all the questions so far. If any of the attendees have any last minute questions, please do either type them into the Q&A feature or raise your hands and we will answer them before hopping off.
Hi,
Sure
can you hear
thing,
me?
go ahead. Yep, we can hear you.
Okay. I just question that this recording will be sent to us. Can we view this recording later on also as well? Because I joined a little late, so.
Yep, we will be sharing the recording within 24 hours of this session concluding.
Okay. And this examples and everything, you will send us an email with the links to the this slide plus the
notebook.
example. Yeah.
Yep, the link to the notebook and slides will be included in that email as well.
Okay. And I just want to know one more strategy, like what is the norm? Like so you talked about the history and all this caching, right? But that is like, okay, a question is asked and the history and everything is answers and everything is kept as of that particular moment. What about the future data which is coming in, right? Suppose more data is coming in and more data is entered into the vector database. So how does that work? Because now maybe some more additional documents may closely match the answer to the question.
Good question. So there's an answer in two different use cases here. For the RAG use case, as soon as you update your documents or as soon as you create new documents in that index, the retrieval will use those documents. So if you were just rerunning the same question with a newer set of documents, with more documents, with updated documents, you will get the updated results as of this current moment. That is one thing, because the index is continually being updated.
Okay.
For the semantic cache, what you can do is set some kind of expiration. So potentially you can expire some of the documents after a while. So let's say you're updating your documents daily, you can expire the cache at that time that you're updating your documents. For a more live system, it might require other strategies, like knowing which documents have, I don't know, timestamps or tags, and then expire it based on those values. But it depends on the document. But essentially, you can expire those cache results, and then the next time it's being asked, they will be cached again with a new response.
Or is it like we can update the cache as well? Like we know the questions which were asked. Based on that, we regenerate behind the scene.
I'm not sure I understand the question.
Suppose we already know the questions, right, which were there, and that is in the cache, right? Semantic cache. Now the cache result is not having the updated information. Is it something as a batch process or something like that? We run through the LLM, get the answer, and then save the results and keep it ready.
That would work in a similar way.
Yeah. Okay. Just thinking through the strategy, I was just asking something like that.
Yeah, basically you're just adding to the cache. You have more data that's in the cache.
Okay, I got it, right. So is it possible to delete also the entry in the cache, apart from expiry? Like if I want to delete?
Yes.
Okay.
Absolutely.
Okay, thanks.
All right, any last minute questions? Going once, going twice, going 3 times. All right, folks, thank you very much for hopping on today's session. Thank you very much for replying to all of the polls. We really appreciate it. And we hope you have a great rest of your days. Thanks again.